Thanks for connecting to this seminar of the working group on active B stars. Before we get started, I just want to remind everyone that these talks are being recorded and are then made available on the YouTube channel. The videos are unlisted, so you actually need the full link to be able to access them. And the links to the videos are available on the seminars page of the Massive Stars Commission webpage. So you can find the previous recordings on there, and Dr. Shao's talk will also be available on there probably in a couple of days. So we're just about to get started. It's my pleasure to introduce Dr. Yong Shao. Dr. Shao obtained his PhD in astrophysics from Nanjing University in 2015, and then worked as an assistant researcher for 4 years. He's currently an associate professor at Nanjing University, and his research focuses on the physics of compact objects, binary evolution, and population synthesis. And so obviously this is what he'll be telling us about today. I would ask, if you're not the speaker, can you please mute yourself so that there are no extraneous noises during the presentation? Great, thank you so much. So Dr. Shao, without further ado, please take it away.
Yes, thanks. Oh, okay. Hey, hello, everyone. I'm Yong Shao for Nanjing University, and it's my great honor to be here and have a talk. Thank Alex very much for invitation. Today, my topic is population synthesis of galactic B stars. This is the outline of my talk, including a short background, the observational clues, and just theoretical models of B star formation. And then I will talk about our population synthesis results. And finally, I will give an outlook and a summary. B stars, here I mean classical B stars. They are rapidly rotating B stars with equatorial velocities near their Kepler limits, and their optical spectrum displaying H-alpha emission lines that originate in a circumstellar decretion disk. So B stars are named after B emission line stars. There are 3 channels proposed to explain the formation of B stars with rapid rotation. The first one is that B stars are rapidly rotators since the star formation. And the second one is that B stars are mid-sequence stars. At some stages during stellar evolution, as angular momentum transfer from the core to the envelope. This is to involve a single star channel. And the third channel is that B stars are mass gainers or stellar mergers due to angular momentum transfer during binary evolution. This is a binary star channel. And next, I will talk about the observational clues on B star formation. From observation, the fraction of B stars among B stars can reach as high as 20% to 30%. So this is 2 authors proposed that B stars may be born as rapid rotators. However, according to stellar rotation sensors of B stars, it is found that most young B stars have rotational velocities well below the limit for B star formation. So it was concluded that only a small fraction of B stars are likely to be born as rapid rotators. And for the simulation of single star evolution, B stars can be produced at the end of the Mach sequence. So it is predicted that the B stars in young star clusters should stay near the turnover region in the HR diagram with a narrow magnitude range. However, the observed B stars in young star clusters cover a wide magnitude range. So this indicates that binary interaction should be important to produce B stars. And in addition, for rapidly rotating single star models, if single star can evolve to appear as B stars, these B stars are expected to have high nitrogen abundances due to rotation-induced mixing inside stars. However, the majority of observed B stars in the larger magnetic clouds do not have high nitrogen abundances. So this is two results indirectly sports that binary interaction may dominate the formation of B stars. Okay, next I will list some more evidence to support a binary star channel for the B star formation. Firstly, many B stars have been observed in binaries. For B plus hidden star systems, they are also known as B plus subdwarf OB star binaries. In the Milky Way, about a dozen of such binaries have been identified. And for B plus white dwarf system, until now, none of such systems has been confirmed in the Milky Way, but 6 such systems or candidates have been detected in the magnetic clouds, which are listed here. It is interesting that there's a special type of B stars. They are called gamma kiss stars. The gamma kiss stars are emitting hard X-rays, and in the Milky Way, there are about 2,000 gamma kiss stars. Previously, we don't know gamma kiss stars are single B stars or B stars in binaries until recently. The observations of radio velocities indicates that gamma kiss stars are actually binaries. And furthermore, gamma kiss stars are proposed to be B plus white dwarf system. Or the idea of white dwarf is very hard. Okay, for B plus neutron star systems, they are also known as B X-ray binaries. The neutron star is capturing the stellar wind of the B star and emitting X-rays. In the Milky Way, there are about tens of B X-ray binaries have been detected, and also about tens of such B X-ray binaries are known in the magnetic clouds. For B plus black hole systems, there are 2 such systems known in the Milky Way. The first one is MWC 656. Also, recently this binary was argued to be or B plus helium star system. But next I will list some other evidence to support a binary star channel for B star formation. For runaway B stars, they have high space velocity. The frequency of runaway B stars is consistent with all of them being disrupted from post-mass transfer binary. And there's another evidence is that if for single B stars, they will have an extended decretion disk. Otherwise, if the B star have a binary companion, the decretion disk will be truncated by the companion. So for B star in binaries, there's a spectral energy distribution will show or turn down. So for a well-studied sample, almost all B stars are observed to show the turn down of spectral energy distribution. So it is possible that almost all B stars have a binary companion. Hi, Alex.
Yeah. Yes. So I think it lagged a little bit there, and we lost your screen.
Yes. Okay. Can you see? Thank you.
Perfect. Yeah. So it was just when you were about to start the third point there.
Yeah.
Okay.
Oops. Okay, you single stars can produce B stars. We expect that some B plus B binaries should exist when one of the two B stars evolves to be a B star. However, until now, none of such B plus B binaries have been detected. So until now, more and more evidence supports that binary interaction will dominate the formation of B stars. Okay, next I will talk about the theoretical models on B star formation in binaries. Here I show a general picture for the formation of B stars. Involved from a primordial binary with two mid-sequence stars. The binary first experience a mass transferring argue phase. After this phase, the primary star will lose its hydrogen envelope and leave behind its helium core. The post-mass transfer binary will contain a Be star and a helium star, where the helium star involved to be a compact object, could be white dwarf, neutron star, or black hole. At this time, this binary is a Be plus compact object binary. And we want to stress that the evolutionary products of Be star binaries are related to many important astrophysical subjects, such as the formation of X-ray binaries, subcompact objects, supernova explosions, and gravitational waves. So understanding the formation of Be star binaries is important. Oh, okay. Next, I will talk about the binary population synthesis. For observation, we actually know the parameter distribution of the primordial binaries with two missing stars. And if we know exactly how binaries evolution, in principle, we can also know the parameter distribution of the Be star binaries, and also there's numbers in the Milky Way. However, there are many uncertainties during binary evolution. Here I list some important, for example, the mass transfer stability during the mass transferring argue phases, and the supernova explorer that forms neutron stars or black holes. So, based on different assumptions and treatment of these uncertain processes during binary evolution, different groups have different predictions. It is predicted that from only a small fraction to about half to nearly all of Galactic Be stars can be produced by binary interaction. Next, I will talk about our models. Here I will focus on the mass transfer efficiency.
It seems like we lost you again there for a second, Dr. Shao.
Sorry.
No, that's okay.
Okay. Okay, for model 2,
Dr. Shao, we actually missed kind of the beginning of that slide. Can you just start from the beginning of the slide?
For the beginning, this slide?
Yeah.
Yeah, okay. I'll talk about our model. I focus on the mass transfer efficiency for the argue phase, and we have built 3 different mass transfer models. And in model 2, we assumed that the mass transfer efficiency is 50%. So half of the transferred mass will be accreted by the equator, And in the model 3, we assume that the mass transfer is quasi-conservative. So the mass transfer efficiency is about 100%. And for model 1, we have a physical motivation. So we can see here, we use this equation to deal with the mass accretion of the equator. So the accretion of the equator is rotation dependent on the angular velocity of the equator, here the omega. So if the angular velocity of the equator is close to its capillary limit, the mass transfer efficiency beta is about 0. So in this case, the equator can hardly accrete. In our calculations, we include four factors to control the rotational evolution of the equators. They are stellar winds, tides, mass transfer, and mergers. Stellar winds always tend to spin down the rotation of the equator. But the mass transfer and mergers tend to spin up the rotation of the equators. And for tides, in wide system, tides can be negligible. And only a small amount of accreted mass can spin up the equator to critical rotation. So in this case, the mass transfer efficiency can be very low, and with a value of about of less than about 20%. While for the enclosed binaries, tides are important, and tides tend to spin down the rotational velocity of the equator. Due to the tidal interaction, it will keep the equator with a relatively low angular velocity. So in this case, the mass transfer efficiency is always larger than about 20%. And in the extreme case, for very close binaries, the mass transfer efficiency may be up to up to 100%. So for model 1, the mass transfer rate is not a fixed value. It's dependent on the rotation of the equator. And next, I will talk about the mass transfer stability. Like for the mass transfer in argue binary. For the equator in a mass transferring binary, it may do some response due to mass accretion, since the equator is a normal star, not a compact star. So it may do some response. If the equator accretes slowly, the mass accretion time scale is larger than the sum time scale of the equator. So the mass transfer can happen stably. Otherwise, if the equator accretes accretes rapidly, the mass accretion time scale is less than the sum time scale of the accretor. So in this case, the accretor may get out of some equilibrium and expand. So this may lead to the formation of a contact binary. And the contact binary may be formed by common envelope evolution. So in this case, the mass transfer is dynamically unstable. So whether a binary evolves stably or unstably is dependent on the mass accretion rate of the accretor, and also dependent on the mass transfer efficiency beta. And in the field of binary evolution, the mass transfer stability is usually related to a concept named critical mass ratio. So mass ratio of a binary system can decide the mass transfer rate on a nuclear time scale, or sum time scale, or dynamic time scale. And this diagram shows our calculated critical mass ratio distribution as a function of the primary masses and the orbital period for the primordial binaries. For model 1 to model 3, the mass transfer efficiency beta will increase, especially for wide binaries. So for a thin binary, the mass accretion rate of the donor or of the accretor in model 3 will be higher than that in model 1. So the mass transfer is more unstable in model 3 than in model 1. So we can see that the critical mass ratio in model 1, from model 1 to model 3 will decrease. And the maximal critical mass ratio in model 1 is about 6, and it will drop to about 2.2 in model 3. And in our calculations, we include the results of both the mass transfer efficiencies beta and the critical mass ratios Q, and we have incorporated them into our population synthesis calculations. Okay, next I will introduce our population synthesis results. And this table gives our predicted numbers of Galactic Be stars. We include binaries. There may be B plus Helium star, B plus white dwarf, B plus neutron star, and B plus black hole binaries. We also include single B stars. They may be from disrupted B plus neutron star, B plus black hole binaries due to the supernova kicks. And we also include the single B stars from the merger of two messenger stars. So we find that if two messenger stars merge can produce B stars, they will dominate the whole galactic B star population. And their number have the order of about 10 to 6. For B plus neutron star systems, this diagram shows their number distribution as a function of B star mass. The gray curve represents the observed results. The observed B stars have the spectrum type earlier than B2, corresponding to the B star mass of larger than H mass. And the blue solid curves denote our calculated results. So we can find that only model 2 can better fit the observed mass distribution of B stars. In this case, the mass transfer efficiency is 50%. For B plus Hidden star systems, we expect that in the Milky Way there are about 10 to 5. Here I focused on a binary named LB1. LB1 was originally suggested to have a very massive black hole, and later it was argued to be a B plus Hidden star binary. This diagram shows the number density of galactic B plus Hidden star systems in the B star mass and the Hidden star mass plane for different mass transfer models. The top and the bottom panels correspond to the binaries formed by case A and case B mass transfer, respectively. The colored pixels shows our calculated results, and this is cross denotes the observed sample. And the purple one shows the LB1. So in model 3, the mass transfer efficiency is about 100%. In this case, LB1 cannot be reproduced in our calculations. So if LB1 is indeed a B plus Hidden star system, it's we suggest that it very likely has experienced a non-conservative mass transfer. For example, our models 1 or 2. And for our calculations, we find that the B plus Hidden star population is dominated by the binaries with a low mass B star of mass about 3 to 5 solar mass. However, for the observed sample, their B stars always have the mass of larger than 5 solar mass. Until recently, there a source named Capdraclis. It is the first emitter to red-type B stars with a subdwarf B star companion. The B star mass is about 3.7 solar mass. So there's a problem. There's a problem that why red-type B star in binaries are very real. This is inconsistent with our theoretic predictions. here we should note also that the detection of B plus hidden star binaries is this detection is subject to a serious observational biases. About a dozen of such binaries have been observed in the Milky Way, and here 2 of them have the stripped hidden star in the shell, in the hidden shell phase. This phase is very short. So why we can observe them? And in addition, if FB1 is a B plus hidden star binary, the stripped star is most likely contracting towards the hidden mass sequence. It means that the stripped star still has a hydrogen envelope around the hidden core. So this phase is also very, very short. So a large number of B plus hidden star binaries should exist, but still hidden. And this diagram shows our calculated number distribution of galactic B plus hidden star binaries. The number distribution as a function of the real magnitude of the B stars. So for a Chinese telescope, LAMOST, it has a magnitude limit of about 15. So we expect that LAMOST can detect about 1,000 B plus hidden star binaries in the Milky Way. Okay, for B plus white dwarf system, we expect that there's number is the order of 10 to 5 in the Milky Way, and this diagram shows there's number distribution in the optical period and the B star mass plane. We can find that this population is dominated by the binaries with low mass B star in this region. And until now, none of such binary has been identified in the Milky Way. And, of course, it is possible that gamma kiss stars are B plus white dwarf binary. For B plus black hole systems, this number is expected to have the order of 10 to 100. And this 2 diagram shows there's number densities in the optical period and B star mass plane for models 1 and 2. And here I list the parameter for the confirmed B plus black hole system MWC 656. The optical period is about 60 days, and the mass of the B star has a range of 10 to 16 solar mass. So we can find that only model 1 can produce B plus black hole binaries similar to MWC 656. In model 2, the mass transfer efficiency is fixed to be 50%. So in this case, the minimum mass of the minimum mass of the B star has a mass about 18 solar mass, which is larger than the observed range of this source. Okay, finally, I will give an outlook and or summary. For our calculations, we find that the formation of BE plus neutron star binary and the BE plus black hole binaries involves inconsistent mass transfer models. The former favors model 2. Here, the mass transfer efficiency is about 50%, while the latter favors model 1. The mass transfer is rotation dependent. Here, if we use metal 1 to produce B plus neutron star binaries, we find that these binaries are dominated by the systems with left type B stars, like this case. This case for B plus Henry stars. So we can also find that for B plus Henry star binaries, there's a lack of the detection of left type B stars. This is inconsistent with our theoretical predictions. So some physical processes is missing in our calculation, or can left type B stars efficiently form in binaries? Okay, here I want to stress that in our calculations we did not include the magnetic fields. It has pointed out that differential rotation due to mass accretion or binary merger may produce stronger magnetic fields around stars. The coupling between magnetic fields and stellar winds, the so-called magnetic braking, which tends to spin down the rotational velocity of rapidly rotating stars. This will prevent the formation of B stars. And from observation, none of observed B stars showed the presence of a strong magnetic field. And here this diagram shows the parameter distribution for some arco binaries. These binaries are in mass transferring. The M1 is the mass of the equator. P is optical period. Omega is the angular velocity of the equator. So for this is argue binaries. For this is black dots. The equators have the mass of less than about 7 solar mass. They belong to this type of B stars. And there's angular velocity have a relatively low values. So for this is relatively low angular velocity can be explained due to the existence of magnetic fields. So it is possible that the lack of the detection of left type B stars in binaries is due to the existence of magnetic fields. However, the modeling magnetic fields is very complicated, and we don't know whether all argue binaries or argue phases can lead to the formation of strong magnetic fields around the equators. In the future, we may include the role of magnetic fields to study the formation of B stars, but it is very hard. Okay, finally, I gave a summary. Both the observations and our calculations show that binary interaction should dominate the formation of galactic B stars. Now here I'll give our predicted numbers for B star binaries in the Milky Way, and we conclude that the formation of B star binaries favors stable and non-conservative mass transfer. Okay, I stop here. Thank you very much.
All right, thank you very much, Dr. Shao. I'll applaud on behalf of everyone. So thank you for a great talk. We have quite a bit of time for questions, so that is great. So I'll open it up to anyone who would like to ask a question. Either drop it in the chat, or you could just unmute yourself and ask your question. So maybe I'll kick off with a quick question. So it was just regarding the accretion stability. So you mentioned the critical mass ratio. And so I was just wondering, how exactly do you implement that in the simulation? So do you just not consider the mass ratios that are above that? Or do you have some sort of implementation for the unstable mass transfer?
Yes, I could consider the mass transfer stability due to, and then we consider the response of the equator due to accretion. So, and what's your point?
Oh, so I was just wondering if you had a bit more details about how it's implemented.
Oh, actually, we use the temperature code, the code stars to do these calculations. Yes, and we consider 3 different models for mass transfer. In models 3 and in models 2 and 3, the mass transfer is usually fixed to, or usually to have a fixed value. And the models 1, the mass transfer we have physical motivation, and the mass transfer rate is assumed to be the rotation dependent. So using these assumptions, we can use the code to obtain this is the critical mass ratio, and when we obtain this is the critical mass ratio, we can fit this is different curves and incorporate it into my population synthesis code, or use a last code to do the population.
Okay, thank you.
Okay.
Any other questions? So actually, one thing that was of particular interest to me was the magnetism. So I know you mentioned that you might try to include it in future versions of your code. Do you have a bit of a preview of how you might go about doing that, or?
Use mechanism of the stars.
I'm sorry, I didn't quite get that.
So you use how to do the magnetic fields. It's hard.
Okay.
I try you use MESA to calculate the production of magnetic fields due to dynamo. Maybe I'll consider the effects of dynamo.
Mm-hmm.
Just I did not do this. Maybe I'll consider this in the future.
Okay, great. We have two questions. So I saw Henrik's raise his hand first, and then we have a couple of questions in the chat. So Hybe, do you want to unmute yourself?
Yeah, hello everyone. Thank you very much for this very nice talk. And you had a very strong outline of how the rapid rotation of these stars come about. But BE stars show this intermittent H-alpha emission. I mean, that is not explained by its origin. Could you comment on that?
You see the origin of the rapid rotation?
No, I mean, you outlined where the rapid rotations come from, but BE stars are found by its H-alpha emission, which appears and disappears. Yeah, could you comment on the mechanism why these stars behave like that?
Sorry, B star are what?
The H-alpha emission.
H-alpha emission. I know it's from the disk, and.
But the question is, why does the disk sometimes appear and sometimes disappear?
Oh, disappear and disappear. This may be related to the active. Yes, you're right. For B extra binary, I know little about the physics of the decretion disk. So maybe it's related to the. I just guess it may be related to the activity of the star activity. I don't know.
You mean the activity of the companion? Is that what you're implying?
The B star is themselves. Like in B extra binaries, just type 2 outburst. I know little about this.
Okay, for now, good for now. Thank you very much.
Thank
you for your talk.
Okay, so we have two further questions in the chat.
Okay. Yes.
So I'll just read them out loud. So the first one is from Myron Smith, who asks, so he says, nice talk. You really summarized the routes and channels by which B stars form. So for observers, generally a B star is an early B star, namely bounded by spectral types of about B0 and B3. Are these the spectral limits that you mean to imply when you refer to them?
It's early. Yes. Are these spectral limits you mean to imply? I don't understand.
Yes, so Myron, if you want to unmute or if there's any clarification.
Are these the spectral limits you in the ER calculations?
Sorry, this is Myron. I couldn't find the mute button here. I didn't want to confuse the issue. You talk reasonably as a binary evolution theorist in terms of stellar mass, and we all understand that. But in terms of, I'm just asking a very simple question. but generally, when you plot the distribution of BE stars, accepting Algol stars and some other what we would call in the classical BE star group oddball stars. Generally, it's bimodal. You have an early peak in early B stars, generally around B0 to B3, and then a smaller peak around B7 to B9 or so. And I was just wondering if you were confining yourself to those limits.
Yes. I can say that in our calculations, we have a definition for the B star. So we defined the B star have with a mass 3 to about 22 solar mass, which corresponds to the spectral time of the range about A0 or B9 to about 09. So from the observation, yes, there's a peak about in the range of B0 to B3. Yes, as I explained in our talk, maybe the magnetic fields can lead to the lag.
I think you answered my question. You're talking about more or less a uniform distribution of spectral types in your population synthesis. Thank you.
Yes, thank you very much. Yeah.
Okay, we have one more question and a bit of a follow-up. So Robert Clement mentions that the nature of MWC 656 has been challenged, and it might just be another B plus subdwarf O star. And apparently that appears in the conference contribution, and Yao adds on whether, wants to know whether the rebuttal of MWC 656 as a black hole binary poses problems to the models or not.
Yes, I have shown in this slide. Yes, the MWC 656 is probably or B plus subdwarf O star binary. Yeah, yes. Thank you.
Okay.
Okay.
So we might have time for one last question before we wrap up. Okay, well, with that, I would just like to thank you again very much, Dr. Shao, for this nice presentation, which will be made available on YouTube. And just as a reminder for everyone, this was our last seminar before the summer. So we will be resuming in September. So thank you, Dr. Shao, for closing us out for the academic year. Also, thank you for connecting at the time that's a bit late for you, I know, in your time zone. But we definitely appreciate the efforts. And you'll all be hearing from me sometime in the late summer for the September seminar. So thank you everyone for joining, and have a good rest of your day.
Yes, thank you very much. So